Just like Jess had done, my background is in ore geology, and so what I'm hoping to do is take some of the techniques that we use in our field and kind of apply them and some of the very different approaches we have to looking at geology and see what can that tell us in the astrobiology field. So again, we have a lot of corporate sponsors, mostly because they let us access to their field site. Right. So to start off, I'm going to be talking about Archean sulfate in particular. And so when I'm talking about Archean, I'm talking pre-2.4 billion years. And this is the big disclaimer alert. So some of the earlier talks, you've heard about the great oxidation event, the rise of oxygen at 2.4 billion years. I do not fall under that school of thought. And so what I'm actually presenting here is showing some of the techniques and actually one of the ways we've gone through and done some modeling to kind of say why we don't put that rise of oxygen, and particularly some of these other interesting redox-sensitive elements, why we don't believe that falls at 2.4 billion years. So in particular, I'm going to be talking about sulfate. We care about sulfate, very important for biology, very important for a lot of the redox chemistry that we're interested in, and really important for making shiny metals. So current consensus right now is that if you have this anoxic Archean, it's really hard to have sulfate concentrations greater than about 0.1 millimolar. That's based off of things like sulfur isotope evidence. That you just simply, if you look at the Archean, it should be hard to get that sulfate concentrations greater than that. However, when we start looking at the actual geologic record, there starts to be some major problems. First and foremost, this is the Dresser Formation. It's 3.49-ish billion years old, and it's a multi-million metric ton barium sulfate deposit. And that's very hard to do if you have very little sulfate in your oceans. Doing the calculations, if you take about that much, it requires almost an entire world's ocean to evaporate to make that much of a bedded salt bed. So that's one problem. The other thing is from our actual ore deposit itself, I'm working on a hydrothermal system that I'll get into, but we also have lots of barite in our stuff. So this is an XRF image. The green sections is where we're going to be seeing that barium sulfate, and you can see it's not equal to pyrite, so there's some interesting fluid chemistry of evolution kind of showing up there. So in particular, I'm interested in volcanogenic massive sulfides, VMS systems. Unlike Jess's system, where it's actually dealing with magma getting some exposure, our system really doesn't actually make real contact with any liquid rock. It's just heat that's percolating through seafloor. So the way a VMS system works, they're analogous to the black smokers that everybody has been talking about. What's happening is you actually have ocean seawater percolates through fractures in the rock. As it's fracturing through, there's some intrusive body, be it a dike, be it a mid-ocean ridge setting, something like that. That's generating an amount of heat. That's going to actually drive that water through, get that big circulation. And as that water moves through, we get all kinds of interesting reactions. Some are just simply moving metals, actually making the massive sulfide that we're so interested in mining. But some of the other stuff is actually doing interesting redox chemistry. So one of the very, very important reactions for VMS systems, it generates a lot of the sulfide that's actually in that massive sulfide, is seawater sulfate. As it comes in contact with ferrous iron in these rocks at above 250 degrees, if there's lots of ferrous iron, which these are basalts, that ferrous iron will actually become ferric iron, and that seawater sulfate will actually become sulfide. And so when you get that mutual thermochemical sulfate reduction, you actually will get halos where you actually get some amount of increased ferric iron in these rocks, and you'll get lots of sulfide in return. So the actual site that I'm interested in, it's known as the Panorama District. We're way up here in the far northwestern end of Western Australia. The actual district is actually a cluster of multiple VMS systems. And what's beautiful and really rare about this is it's actually cut on profile. So usually when you're looking at these deposits, unless you're actually in a mine, you don't get to see what the circulation cell looked like. But in this case, if we actually look at the strat column, we would have laid down the basalts and everything like that that was being circulated through first. And then this big Strelly granite punched up through. And as it did so, it tilted everything about 90 degrees. And that's really the end of where the major deformation stopped. So we actually have this beautifully preserved side view of these systems. So we can actually look at the hydrothermal circulation cells. Now, what's also important to know for it's a geology, we get the obligation, to show a fieldwork photo. What a mining company describes as a road is somewhat different than what you might describe as a road. So it's an interesting place to do fieldwork and collect samples. So what we've done, though, is we've actually collected large amounts of samples, and we've analyzed them for ferric-ferrous ratios. So, right, this is kind of weird, right? We're going to be looking for sulfate concentrations, but we're using iron. Well, we're coming back to that actual reaction that we were talking about that's so important in VMS systems. Now, we think we actually have a pretty good handle on VMS systems. When we work with ore deposits, because there's so much money in the line, we understand them pretty well, and we're pretty sure we actually have a good handle on not only the processes, the temperatures involved, the reaction rates that are involved. So we think we can actually do a lot of modeling going forward. So if I have a map like this where I've actually been able to say that, yes, there's actually an increase in the ferric-ferrous ratios around what we've actually deemed and a lot of authors have worked on and identified as the hydrothermal circulation cells, that maybe we can actually use this ferric-ferrous enrichment to actually say how much sulfate was required to circulate through the rock, and therefore what was the seawater sulfate concentration. So alteration geometry, fortunately, like I said, we have this nice profile view. So what we actually can do is we can kind of confine these slabs. And if we do a simplified strat column, most of our circulation occurred in these andesite basalt layers. They're roughly tabular, and frankly, for it being 2.4, we're going to start assuming some simplified geometry. It's something we do for a lot of these type of ore systems. We take simple shapes. So in our case, we chose a cylinder. It's a fairly simple, it's a fairly accurate assessment for doing these type of things. We've done them for a lot of these type of ore deposits. So what we're doing is we're going to assume a cylinder. Our circulation cell is about 6 kilometers in diameter. And so that cylinder of rock has some starting ferric-ferrous ratio. In our case, we took pristine back arc basin basalt that has a ferric-ferrous ratio of about 0.2. It's a pretty fair assessment. People have done a lot of identification on these basalts. Starting off with that, it's an assumption, but it seems like a pretty safe assumption is that's what our starting iron oxidation state is. So what's going to happen is more and more seawater is going to circulate through this rock as time goes on. And as that's happening, you're going to actually start increasing the iron oxidation state. So from the actual data that we've measured, we have a final ferric-ferrous ratio of about 2.5. So what we've actually done is we can say, to get from here to here, we have some huge number of moles of iron oxidized. All right, the number is not as important, but we need it for our calculations. So if we go back to our favorite reaction here, what we can do is we take the number of moles of iron that were actually oxidized. We can come back and derive out how many moles of sulfate were required. Now, that gives us a total amount of sulfur. That does not actually give us actual ocean concentrations. To do that, we actually need to start thinking about how much would actually have to flow through the rock. So when we do these hydrothermal systems, just using sheer volumes of rock, really cumbersome and bulky and doesn't make a lot of, it doesn't work really well in your head. So what we use is what we call water rock units. So water rock unit is the mass of water to flow through the same mass of rock. So it's just an easier unit to put in your head. And so what we notice is, and as you might expect, that at very low sulfate concentrations, it takes more units of this water at low sulfate concentrations to flow through it to generate that observed alteration. However, if we start increasing that sulfate concentration, now it's starting to take smaller and smaller water rock ratios. Now we're starting to actually, can we kind of limit it in? So again, that doesn't actually, this chart, I have this highlighted, but I'll show you why. If we actually go to the actual deposits and we start looking at the alteration minerals, what's really nice is we can actually say how much water has flown through there at temperature. So when we actually look at the alteration minerals, we can say that there was probably not more than 60 water rock units flowing through that body. There's simply the clays and the things we see there. If you had more water flowing through it at higher temperatures, you simply would not have preserved the mineral textures we see. So using that as our limit, well, we see that just based on the hydrothermal alteration, that we have a limit of about 1 millimolar sulfate for the water that was flowing through these systems. Now, there's another way we could go about looking at this. I had mentioned that these hydrothermal systems, these VMS deposits, are driven by some sort of intrusive heat body. So if we take, again, our nice simplified cylinder there needs to be some volume of intrusive below it that's supplying the heat that's actually going to be driving the system. Now, Larry Cathlas, who's done a lot of work on these systems, he's done all the very, very complicated math, but it really comes down to, at the end of the day, to heat 1 kilogram of seawater to 250 degrees, which is the requirement for this reaction to go forward, you need 0.7 kilograms of melt. So if we go back to looking at the actual water rock ratios that we were talking about, depending on sulfate concentrations, we can actually say how thick of the volume of melt has to be to actually drive this hydrothermal cell. So if we're at sulfate concentrations less than, say, 5 millimolar, you all of a sudden need a granitic intrusive that is now more than 10 kilometers thick. Well, we've mapped and we've drilled the Strelly granite. We know it's not actually larger than 10 kilometers thick. So that right there is actually providing a limit that you needed to be able to actually flow water through this body and not quench the system. So that's suggesting that we're at least 5 millimolar sulfate in this contemporaneous Archean seawater. Now, that's assuming at 250 degrees. If we base on some of the metals that we see there, things like copper that require higher temperatures, odds are we're actually going to probably move this even towards greater sulfate concentrations in this contemporaneous seawater. So really, what did we really see when we were going through these sites? The first thing and foremost is, if you're interested in Archean sulfate, there's extensive sulfate mineralization. It's all barium sulfate, but frankly, if you think about things like gypsum, they're too soluble. They would not have been sitting around for 3 billion years. We've observed very large ferric enrichments, and they seem to be the result of sulfate reduction. And when we looked at the actual alteration patterns in some of the thermal modeling, we actually see that we're probably looking at least 1 to 5 millimolars of sulfate, which is an order of magnitude greater than what people are proposing that should exist in that pre-rise of oxygen Archean. Now, kind of a teaser, something I'm not presenting here yet, but if we actually look at some of the other elements, things like uranium, tungsten, chrome, that are also redox sensitive, we actually see similar patterns to what we've seen here for the ferric iron. So it's not something that's alone in a vacuum. And so I really liked the idea yesterday of doing this takeaway message. And really the takeaway message that I have, and it's not just from this site, but it's also looking at things like the banded iron formations that are all over Australia, and some of the other interesting chemistry of these VMS systems, not just in Australia, but also in Canada. It's increasingly looking like the Archean ocean chemistry, at least in the redox element state, is actually a lot like the modern ocean, that at least the rise of oxygen as we know it might not have happened at 2.4. There obviously was a rise of oxygen, but we need to do a little bit more fine-tuning as to exactly when it was, and can we make can we choose a date that includes a lot of the geologic evidence that kind of stands as a major impediment to putting it at 2.4. Thank you.
Nicely done. Do we have any questions? All right.
We have one online if you want to take that in the meantime.
Sure.
So many here. Why did you use Backart basin basalt as your starting composition?
Right.
Also, what created the acidic solutions you mentioned?
So Backart Basin basalt, the reason we've chosen Backart Basin, there's actually been a lot of geologic work on this site because there are 2 economic grade. And when people have actually looked at some of the petrology, we see signals that are very, very indicative of what we'd expect to see in a back arc setting. In addition to that, a lot of these VMS type formations, particularly with the elemental concentrations of zinc, lead, and copper, this VMS has like the chemical footprint that we like to consider typical for a back arc setting. I didn't recall what was the second bit. Right, so acidic solutions are going to be a byproduct of flowing the solution through the rock. You're going to pick up a lot of either HCl or it's a couple different acids you're going to get from actually interacting with the water. So you're starting with normal seawater. It's Archean, it's probably at least a log unit more acidic, but it's actually just reactions with that surrounding ground through that rock that's actually generating an acidic solution.
So people typically interpret the isotope record from the Archean as there was insufficient marine sulfate for there to be isotopic fractionation by microbes, but you're saying that the concentrations were sufficient for that fractionation despite the fact the isotopic evidence doesn't support that. I'm sure you've heard this question before. I'm just wondering how you reconcile that with your findings.
Well, so the big question is what isotope record are we looking at? So the bigger question when we're looking at life is we're looking at the 34 sulfur fractionation. And that is something that actually is interesting. So if we actually look at these VMS systems, or any of these systems, if we're lucky enough to actually have sulfate preserved as well as sulfide, there's some fractionation between them. So in the modern environment, the fractionation between sulfate and sulfide is usually around 20 per mil in an active VMS system, maybe 30 per mil. In this case, as we start moving towards the Archean, you are correct. it starts narrowing down. And there is a lot of work that we're doing as to what is the component of that, or what is the source of that. It could be mixing. You could have a larger component of actual just igneous sulfides leaching from rock. There's a couple different things that could actually be helping form that. People have done things like if you increase reaction rates, you can also drive them together. I'll admit that the sulfur isotope record is not my absolute area of expertise. Mine's more just the bulk chemistry, but I can say that if you're really, really interested in it, the guy right behind you is doing a poster doing exactly what you're interested in the Archean sulfur record.
All right, pressure's on. Cool, I think we're gonna move on. Thanks, Jamie.